hacer.
Okay, so I've got a sample question paper. This is from the actual exam board, so they're the people writing the questions. They know the style of questions they're writing, the kind of thing that you should be expecting in an exam. So it's always good to make sure you're going through all the sample ones. And people sometimes miss these ones out and just do the like past papers rather than samples. But the samples are just as good and definitely good for extra practice. So let's get on to question one then. So I'm being asked, sorry, for percentage uncertainty over here. So the first thing I do when I've got a percentage uncertainty question is I look at the formula that I've been given and are there any additions in here or not? And there's no additions, which means or additions or subtractions, which means everything is essentially or can be reduced to a multiplication. So because it's that, I just know I can use the easy method of adding the percentage uncertainties together. The hard method, or the long, not really hard, but the longer method will work for all of them. About, even if there was an addition in there and you have to work out the absolute and all that kind of stuff. And if you want to practice this using that method as well, then you can do so. And if you need some help from me, like going through that method as well and using this as an example, then obviously ask me. Because it is worth practicing both ways as much as you can, because it's definitely going to come from the exam, and you might as well just take these marks. But because this is one where we can use the easy way, for the video I'm just going to do it the easy way, the quicker way, and then like I said, if you need any extra help with it, then just ask me. Okay, so I'm just going to work out the percentages of them individually. So what's the percentage error in AL? So 1 divided by 100 times 100 is going to be 1%. The percentage error in the diameter is going to be 2%. And then the percentage error in the mass is going to be 0.5%. Now let's take a look at the formula and see what I can do. So 4 is just a number, so there's no error in there. What's the error in m? We just worked it out, is 0.5%. What's the error in pi? There's no error in pi. What's the error in d? 2%. So I'm going to write that down, but it's d squared, which is the same as d times d. So there's another d with 2%, and the error in L is going to be 1%. So now I'm just going to add these all together. So 0.5 plus 2 plus 2 plus 1, and I should get the answer of 5.5%. Is that an option? Yeah, it is. It's D. So excellent news. I have got a mark. Okay, now for question 2, just remember the philosophy that if it just says which statement is correct, don't just pick the first one that looks correct, because they purposely put tricks in there that they all will kind of seem correct. So I want to go through all of them, and if I think it's incorrect, I'm going to say why it's incorrect. So which statement is true about the electrons? So they drift towards the negative end of the cell. Well, I know that they don't. They go towards the positive because electrons are positive, so I can rule that one out. That's nice. They've got random speeds because of collisions with other electrons. Now that seems reasonable. I might think that one's true, and if I didn't use this method, I would possibly tick that one and go, oh yeah, safe, the answer is B. But it says here collision with other electrons. They don't collide with other electrons, they collide with their ions, so that's not true. They travel through the wire at the speed of light. I should just know that they don't. Nothing moves at the speed of light apart from EM waves. And then now I'm hoping that because I've said all of these are wrong, D is going to be right. They collide with vibrating copper ions. Oh yeah, they do. We covered that in B. So yeah, this one's right. And fantastic news, I have got 2 marks already. Okay, so even just looking at this diagram, I can see that it's an internal resistance question, because I can see that they've got like that little dot thing there that I can see there's internal resistance within the battery. And then, I mean, to be fair, it even says it. So even if I didn't notice from the picture, I should be able to read by now. So what's the internal resistance? So with all electricity questions, I always do the same thing. Just do whatever values I can, just say what I know, and hopefully I can identify the right formula from there. So it says the switch is open, the voltmeter reading is 9. So why is it saying the switch is open? Well, I should know that when I put a voltmeter across the battery or the cell, when there's no current flowing through the circuit, that's the EMF. So I know that 9 is going to be the EMF. And it even says that the ammeter reading is 0. Whoops. So when it's closed, the voltmeter reading is 6 and the ammeter reading is 2. So now I know that, okay, I've got some like 3 volts or lost volts. That might be useful to me, I'm not too sure. And it says the ammeter reading is 2. And I've basically got the voltage as well now. So what's the formula that I'm going to be using? Well, because it said internal resistance, I'm already pretty happy that the formula I'm probably going to use is E equals V plus IR. What am I looking for? I'm looking for little r. So have I got everything else? Well, I've got E as being 9, I've got V as being 6, I've got I as being 2, and little r is what I'm looking for. So I can just rearrange this and I can say 3 is going to be equal to 2r, Therefore, R is going to be equal to 3 over 2, which is 1.5 ohms. And I'm going to hope that this is one of the options, and it's option A. So I'm going to write down A, and I have got 3 marks out of 3. Fantastic. Okay, so I've got 3 statements here, and I've just got to say whether they're all true or false. So let's use that tick or cross method and just see. So all photons travel at the same speed in a vacuum. Yeah, they do. I should know they travel at 3 times 10 to the 8. Photons have no charge. Yeah, that's true. That's fine. And then the energy of a photon depends only on its frequency. Well, the word only here is making me a little bit suspicious, so maybe I've just got to pause and think, is it actually true? The energy of a photon depends only on its frequency. Well, what does it depend on? E equals hf. So I know that h is a constant, so therefore it is only on its frequency, because what if it had like when we're talking about like wave theory, and we know that the energy of a wave also depends on its amplitude and stuff like that. Well, that doesn't apply here. So it's just testing, do I know the difference between wave theory and quantum theory? So does it depend only on its frequency? Yeah, it does. You could possibly argue, like, or some people might be saying, oh, well, what about wavelength? Well, that's because wavelength is linked to frequency, so still, it still depends only on its frequency. So I'm happy that they're all correct. And is there an option that says 1, 2, and 3? Yeah, there is. So the answer here is A. Okay, so number 5, again, we're going to do the same thing, that I'm going to put a tick or cross next to each of them. I'm going to hope, because it says which statement is correct, I'm going to hope I've only got 1 tick at the end. So the electrons travel as photons through the metal. The word there that's making me suspicious, photons, they travel as waves through the metal. So that is incorrect. I'm going to put an X next to it. B, the electron's got a wavelength of about 10 to the minus 10. Now, I haven't got any values that I can actually calculate it, because if I had values, I'd be able to calculate and I should be a professional and pronounce it properly, de Broglie, but I mean, written de Broglie. I could be able to possibly calculate the de Broglie wavelength of it, but I don't have any values yet. Maybe I can make some reasonable estimations from stuff that we know, but B could possibly be true, and we can come back to it later and see why it is or isn't. The electrons are diffracted by holes in a metal. I just know that they're not. I should know that they're diffracted by the spaces between atoms. So I'm going to put a cross next to that. And it says the electrons repel each other to produce the diffraction. And again, that's, if I think that I'm just misunderstanding what interference is. They behave as waves, and therefore they're going to be interfering. So that's going to be wrong. So I'm pretty certain that A, C, and D are wrong. And first I said that I was a little bit iffy about B, and I haven't got any numbers to do any calculations. But how should I know that B is going to be right? Well, there's ways I can do. The first way that we said is that like from reasonable estimations that we've done in the class about how much does it get accelerated through and so on. So what's the rough speed, and then calculate the Bohr wavelength maybe. But the other thing that I know, and C kind of gave me a clue to it as well, option C, is that I know that diffraction is going to be occurring when the size of the wavelength is comparable to the size of the gap. Now, I should know, again, from the reasonable estimations that we're doing in the lessons and stuff that you expect to know, that the about 10 to the minus 10 would be the gap between the atoms. So therefore, that's another reason why I think B is correct. So I am putting B down for that one, and yeah, I have got the mark for it. Okay, so question 6, I really love these questions because, I mean, there's a lot in there that we can do. It's very, very nice. The only thing that could possibly make this question even better is if they didn't give me the wavelength of light, but they just gave me the color, and they said like red light or blue light or green light, and then I should know, I should be able to estimate the wavelength of it myself. But because they're using yellow, they're kind of telling me the wavelength of it. But I mean, they've given percentage here, they've given me power, and it says how many photons. So I mean, this has got everything that you could possibly hope for in a question. Using a formula, and also coming up with your own formula, and like trying to understand what's going on. So let's have a go. Okay, so the first thing I know, because it's giving me the wavelength and it's about photons, I know the formula we're going to have to use is E equals hc over lambda. So I'm just going to put the numbers in the equation. I can't bother to write them all out, but basically I found out the energy of one photon is going to be 3.37 times 10 to the minus 19 joules. Okay, well, what can I do with this information now? I know that the sodium lamp is rated at 40 watts. And here it also says per second, so that's giving me a clue that it's going to be something to do with the power. So 40 watts means it's going to be 40 joules per second, but it's only 12% of the power is emitted as yellow light. So the total energy that's going to be emitted as yellow light, so energy as yellow, is going to be 40 watts per second, which is 40 watts, which is 40 joules per second, multiplied by 0.12, which is the efficiency of the lamp. So 40 multiplied by 0.12 is 4.8. So I'm going to put 4.8 joules in here. Okay, so now if I know that one photon is 3.37 and the total energy I'm looking for per second is 4.8, how am I going to get the total number of photons? Well, I'm going to have to do 4.8 divided by 3.37 times 10 to the minus 19, and then the answer that I should be getting for that one is A. Okay, so question 7, we've got an electricity question again, and it's again that thing that if there's anything that I can label on the diagram, I'm going to do so. So I'm having a look at the information that I've been given and looking at the diagram, and to be fair, it kind of looks like everything's been labelled on there already. And is there anything more that I can do, anything that I can work out? Again, not really. I could possibly, well, it's a series circuit, so I know that the current going through the whole thing is going to be the same. So I can kind of just get on with the question, really. So how much electrical energy is provided by the charging supply? Well, what's the formula for electrical energy from the things that I've got? Well, I know that electrical energy is V times I times T. And have I got those values in there? Well, I've got two V's, I've got 14 and I've got 12. Which one do I care about? Well, it says how much energy is provided by the charging supply. So that's the one that I care about. So which one is the charging supply? It's 14. So I'm going to put 14 in there. Have I got the current? Yeah, I have. It's 2.5. And because it's a series circuit, I know that's going to be 2.5 everywhere. So I don't need to worry about that. And then 6 hours. Well, I've got to convert that into seconds. So 6 times 60 times 60. I'm going to put that in the calculator. And I know that the answer that's coming out from the calculator is D. So is there anything really that kind of stands out with this question? I mean, there are some values that you haven't used. So I didn't use a 0.8, I didn't use a 12. And it's not very often that they do this, but they do it sometimes, that they will put in some numbers as just as like distractors in there. And this is just an example of when they've done that. It generally doesn't happen that much. Normally, if they put a number in there, you will have to use it, particularly for longer answer questions. But yeah, this is just one of the rare ones where there are just numbers in there that are relevant to me. Okay, so let's take a look at question number 8. So this, it looks like it could be a pretty tricky one because firstly, I don't like its electric potential, and it's just a bit of a pain that, I mean, there's loads of those formulas that look pretty similar. And then, is it QQ, is it Q, blah, 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 whatever it is. So I've just got to make sure that I'm going to use my formula sheet to make sure I'm using the correct formula. Obviously, I don't want to get mixed up with another one. And then what are the things that stand out to me here is that it's giving me the name of a particle, which is an electron. So whenever they give me the name of the particle, I know straight away, I'm going to be thinking, I know the mass, I know the charge. So in my answer, I'm going to either use the mass or the charge or both. And then similarly, it's going to be alpha particle. So the same thing applies. It's the name of any particle. It could be like gold nucleus, alpha particle, whatever. I know the mass, I know the charge. So here I know the mass is in charge of electron and alpha particle, and it's even giving me that there, just, I don't know, in case I didn't know that, but I mean, I should know it anyway. Okay, so the question is saying what's the magnitude of the electric potential, and it's saying at the midpoint, so that's something that's a bit iffy to me as well, between alpha particle and electron. Well, the fact that I'm seeing the midpoint is like, okay, this is going to be confusing, let me just draw a diagram. So I've got my electron, which is over here. So my electron sat there, and it's saying at a certain point, which is 1.2 times 10 to the 5 meters away, over here, this is where the electric potential is minus 1.2 times 10 to the power of 4, minus 4, sorry, joules per coulomb. And it's saying at that point as well, that's where the alpha particle is. The alpha particle passes through that point. So I'm just going to draw the alpha particle right there at that exact same point. So here's my electron over here. Here's my alpha particle. And basically it's saying what's the midpoint between them, or the midpoint between them is over here. Now, I know the electric potential because of the electron at this point is this. I don't care about that point, I care about the midpoint. So what am I going to do? I'm going to go to my formula sheet and just look. I hope there's some kind of proportional relationship or something I can use that's got some information in there. Well, what's the formula? Firstly, I'm going to make sure I use the right one. So it's V equals Q over 4 pi epsilon naught R. Okay, can I look at proportional relationships here and take out the things that are constant? Well, I know 4 pi epsilon naught is always going to be constant anyway, so I can kind of get rid of that, and I can worry about what's going to be constant. Whoops, out of the other two. So I can say proportional to Q over R, and in this case, if I'm talking about just the potential from the electron, Q is also going to be a constant. So this is quite nice now. So I can get rid of that Q, and I can say V is proportional to 1 over R. Okay, so if at this point X that I labeled X, the electric potential is minus 1.2. If I'm at the midpoint, well, I'm half the distance there. So if I'm halving the radius, what am I doing to V? Well, I must be doubling it. I should know about proportionality. So because of the electron, my electric potential at this point is going to be minus 2.4 times 10 to the minus 4. So I've got that there because of the electron, while the alpha particle is here as well, which is causing me a bit of hassle. So let's have a look. So what do I know about an alpha particle? Well, firstly, if it's the midpoint between the two things, I know that the distance is going to be the same. So if the distance is going to be the same, I can just go back to this formula over here and just take out R now, as R is going to be a constant. So I'm going to say V is going to be proportional to Q. And I've got that there. Okay, now what do I know about the charge on a alpha particle compared to the charge on an electron? Well, I know that firstly it's going to be positive, and secondly it's twice as much in terms of magnitude. So if this is minus 2.4, the other one, the alpha particle, is going to be positive 4.8 times 10 to the minus 4. And now, if these two potentials are combining, I'm basically going to add them together. So minus 2.4 add 4.8 times 10 to the minus 4. And what's the answer that I'm going to get? That's going to be positive 2.4 times 10 to the minus 4. And therefore the answer for this one is going to be B. Now, because it's electric potential, I can just use the, like, it's going to be positive, negative, and that was pretty simple for me. If it's asking me about like fields or forces or something like that, I might also need to maybe like draw arrows for the direction or something like that. So I need to be careful about, oh, like if it was talking about the force on both of them, the force from the alpha particle, it would repel a positive particle, so make that one go that way. But then the electron would attract the positive particle, so again it would make it go that way. So I would have to add their magnitudes because they're both acting in the same direction. Before electric potential, I can just use the symbols, and I'm happy that the answer is correct. Okay, so there's a bit of a trick in this next one. They're being a little bit sneaky. So they're telling me that a coil with 3 turns of wire is used in experiments. So they're using that number 3 in there. And then it says the graph shows a variation of magnetic flux linkage with time. Now, every time I see a graph, I know I'm always taking reading from the graph and go, does the area in the graph mean anything? Does the gradient mean anything? And so on. And I look at the axes as well first I'm doing. Well, here the axis says flux linkage. So because of the fact that axis says flux linkage, this has already taken the 3 into account. So what some students might do is go, oh, I'm going to have to like multiply by 3 or something like that. But because I'm being careful and looking at axes, I've seen that it already says flux linkage. So like I said, they were being a bit sneaky by trying to trick students into multiplying by 3. But the graph, by me actually reading the axes on the graph carefully, I've seen they've already taken that into account. Okay, so now it's saying what is the EMF induced across the ends of the coil? Well, what do I know about EMF? I know EMF is going to be equal to the rate of change of magnetic flux linkage. So I've got that over here. Well, as I'm doing with all graphs, basically, I'm going to go, is the does the gradient mean anything? Does the area mean anything? So is y divided by x anything? Is y times x anything? Well, actually, y divided by x is the flux linkage divided by the time. I've checked the units in there, and the unit says milliseconds. So I've just got to be careful with that. And now, basically, I can just get the gradient from this graph, and I'm going to get the answer. So let's have a look at what the gradient is going to be. So what's my change in y? My y goes from 8 to 0, or 0 to 8, the difference is going to be 8. So I've got a difference of 8 times 10 to the minus 4. And then my time has gone from 0 to 2. So I've got a magnitude difference of 2, and that's milliseconds. So it's times 10 to the minus 3. And if I'm doing 8 times 10 to the minus 4 divided by 2 times 10 to the minus 3, I put that in the calculator, and then the answer that it's telling me is 0.4. So therefore the answer is going to be C. Now, on a similar theme to the last one, it's another graph, and I'm just going to be careful of reading the axes so I don't fall for the trick. So again, they're being a little bit sneaky here, because they're saying I've got a graph of binding energy per nucleon, so I've read the axis properly, and the question is saying which has got the largest magnitude of binding energy. So I'm not just reading the top value because it says binding energy per nucleon. Well, it's the total binding energy that I care about. Well, D has got so many more nucleons. that the total binding energy, even though it's got slightly less binding energy per nucleon, the total binding energy for D is going to be much larger. Okay, so this is one that might be a little bit misleading to some students in a certain way, because it's telling you, so what some students might think is that, oh, I've got a 0.7 here and I've got a 0.7 here, so I can like maybe take a shortcut or do something like that. You can't do that for this question, because this is telling me, the first one is telling me that after 1 centimeter, 0.7 of that thing has been transmitted. And the second one is telling me that, well, I haven't gone through a whole centimeter, I've only gone through 0.7 centimeters. So the way that I'm making sure that I'm going to be doing this is I've just got to use the formula, and as long as using the formula, I'm going to get this one right. So what's the formula that I've got to use? If I'm not too sure, I'll just look at my formula sheet to make sure I'm getting nothing wrong here. And this is the formula that I've got. Okay, so I'm looking for the percentage intensity of X-rays transmitted. Well, always with these questions, I've got to be a little bit careful. Is this formula, is this I here telling me the amount that's been transmitted, or is it telling me the amount that's been absorbed? And this formula is going to tell me the amount that's been transmitted. The way that you can kind of think about it and make sure you don't get it mixed up is this formula is very similar to the standard capacitors ones, where the graph is this shape over here. So over time, is the amount of X-rays that are transmitted going to go down, or are they going to go up? The amount of X-rays that are transmitted are going to go down. The amount that are absorbed is going to go up. So because this is showing me that the graph is this shape, that must be the amount that's transmitted. So I've just double checked that. Or, I mean, to be fair, if you've got a good memory, just remember it. But it's always nicer to understand things. Okay, so now I've just basically got to put the numbers in. So it says, what's the percentage intensity? So what's my original intensity then? Well, if it's asking for percentage, my original is going to be 100, sorry. If it asks me for a fraction, the original is going to be 1. Well, this percentage, so my original is going to be 100 times E, which is just E to the power of minus the coefficient. So that's 0.7. And I'm leaving that in centimeters because my distance is also in centimeters. So because they're both in centimeters, I don't need to convert, and then my distance is 0.7. Now all I do is put that in the calculator, and my answer is 61%. Is there an option at 61%? Yeah, there is. Well, the closest one to one significant figure is going to be 60, so therefore I'm going to put that answer as D. If it asked you for the percentage that is absorbed, how I'm getting the amount that absorbed, well, if 60% is transmitted, then I know that 100 minus 60% is absorbed, therefore the answer would be 40%. Okay, hopefully this one's reasonably okay, and if I'm just filling in the numbers like I know about conservation of mass and conservation of charge, I should just be able to fill these numbers in and get the answer right, so how many neutrons are left over. Well, let's do the proton number first, so or the charge number, Z number, whatever you want to call it. So at the start I had 92, and at the end I've 50 of those things have been accounted for. So how many protons must Z have? It must have 42, because now my charge number adds up at the bottom, my Z number adds up. That's a 4, not a 9, by the way. Okay, and then what is my mass at the start? Well, my mass at the start on the left hand side, I've got a mass of 239. On the right hand side, so far, this big 13 means I've got to multiply the whole thing by 13. So I've so far got a mass of 126 plus 13, which is 139. So if I've got a mass of 139, what's the mass that X must have? 239 minus 139. So the mass X must have is 100. Well, if I know X has got a mass of 100 and 42 of those things are protons, it's got 100 protons plus neutrons, and 42 of them are protons. My answer for the number of neutrons must be 100 take away 42, which is going to be 58. And that's an option over here. So the answer for that one is C. Okay, so reading the information in the question for this one, I can see that it's about producing X-rays basically. So I'm going to get I've got a potential difference between the cathode and the anode, and then I want to know what's going to be the minimum wavelength of the X-ray photons emitted. So the energy that the electron is going to gain when it's being accelerated is going to be EV. So I know that's going to be true. I know that the energy of a photon is going to be equal to HF, and I know that the energy of a photon is also hc over lambda. So all of these things are going to be equal to each other. So I can say EV is going to be equal to HF, which is going to be equal to hc over lambda. And in these ones, because all of my options are about the wavelength, I can kind of get rid of that, and it's just going to be about these ones here. Okay, so let's have a look. So it says the minimum wavelength is halved when V is doubled. So I can see here, well, E is constant, H is constant, C is constant. Therefore, the relationship is that V is proportional to 1 over lambda. So the inversely proportional, so yeah, this one's going to be true. The minimum wavelength is unchanged when the temperature of the cathode is increased. Well, that's got nothing to do with it. There's nothing in here about that. So yeah, that's going to be true. It's going to be unchanged. And minimum wavelength is independent of the cathode material. Now, again, there's nothing in there to do with this. And the reason why people might get tricked with this one is because like they might be thinking about work function, but like you should remember when you're talking about X-rays, the work function is negligible. So when it was about UV photons, yeah, fair enough, the work function does matter because the energy of X-rays is just so much larger compared to the work function. It's just irrelevant. It's negligible. So yeah, the minimum wavelength is going to be independent of the cathode material because we can say that all of that energy is going to the photon. So all of these things are true. So therefore, my answer is going to be A. Now, question 14, I think we can just move straight on to it because it's just kind of like a remembering thing. So the force is either going to be strong or weak, and then I've just got to choose what the leptons are. Now, the first thing when I'm doing this question is I'm seeing, like, is there anything that isn't a lepton? That's the first thing I was suspicious about because they might try to trick me by putting something like a proton or a neutron or something because I know they're not leptons, they're hadrons. But there's nothing in there like that, and I've seen that all of these things are actually leptons. So there's none that I can rule out easily like that. So my first thing I've got to have a look at is the force responsible for the decay. Well, I know that it's the weak force that's responsible for it. So the answer is either going to be B or D. I can get rid of A and C, and then which are the leptons that are emitted. And again, when it's a down into an up, I should know that that's a beta minus particle, an electron's going to be given out, and I know that an electron always comes with an antineutrino. So therefore, the answer is going to be D. Okay, so they're being very, very sneaky for question number 15. So let's just have a look at the general approach for these questions first before we worry about this specific one. So I'm seeing that it's about some wire that is into a conductor that's in a magnetic field. And I can see it's giving me the flux density. Yeah, it's giving me the units I would need to convert. It's giving me a current. It's giving me an angle between the field. And straight away I should be thinking, okay, so I'm thinking, is it sine or is it cos? Because I need to know remember it's the angle between the normal and the field that we care about. Now, before I even actually start getting into that and doing all the calculations, let's just have a look at the question itself. It's saying, what is the magnitude of the force experienced by a 1 centimeter section of the loop? Well, the loop is what I mean, because there's a loop, I've obviously got current going around like this. And it says the current in the loop is that. Well, if we just think about this sensibly, whatever answer I got for this side of the loop, I'm going to get the same magnitude of answer for that side of the loop. And maybe some people have realized what the correct answer is now or why is the correct answer if you've already seen it on the mark scheme. It doesn't really matter what the current is. It doesn't really matter what the strength of the magnetic field is because the magnitude is going to be the same here and here. They're going to be in opposite directions. Therefore, the magnitude of the total force that's experienced is going to be 0 newtons. So the answer for that one is going to be A. Okay, so hopefully you've read this question. And I can see there's a graph there. It looks like there's a missing point and there's a missing thing in the table. So I'm probably going to have to fill those in. And if we look at question 1, yeah, it says complete the table by calculating whatever it is. So it's the missing thing that I need to fill in. So I'm just going to put the numbers into my calculator. And I should know the formula for resistance. The only real thing that I need to be careful about here, and to be fair, it should be pretty obvious, is that all of these answer to 3 significant figures. So I've got to round the answer from my calculator to three significant figures to match the number of significant figures in the table. And then that's going to be fine. Okay, and then it says plot the missing point. So it's worth the same mark. So what was the length? So the length was 0.4, so that's going to be over here. And then we said it was the resistance was 5.56. So I just need to be a little bit careful here. So the difference between 5 and 10 is obviously going to be 5. So I know that whole thing is going to be worth 5. How many squares are there? There are 10 squares there. So each square is going to be worth 0.5. So 5.56 is going to be somewhere. So if I go up here, it's going to be somewhere like 5, and then 1.5 squares is going to be like that. Okay, that will be the mark for that question. That will be fine. Okay, now they're being kind of nice for this one, I suppose, because they're saying the students observe the Y significantly hotter. So already I'm suspicious about this. Why are they telling me significantly hotter? Basically, they're trying to make it obvious to me that it's an anomaly and testing that I know what to do with anomalies. Now, even by looking at the graph, I should know it's an anomaly because I can see that that point doesn't match the rest of them anyway. So now, when it's saying, oh, give me the crossing area, blah, blah, determine the resistivity of the metal, I already know that I'm obviously going to have to do like a line of best fit here. So I'm just going to try to, I mean, when you're doing it, obviously use a ruler and all that kind of stuff. I'm just going to do something roughly okay, but obviously I'm ignoring this one because they made it very, very obvious to me it's an anomaly. So I've circled it to show, look how I know this anomaly. I'm going to do my best to draw a straight line of best fit. Don't laugh. Okay, that's rubbish, but never mind. I'm just doing nicer in the exam and I'm sure you'll be fine. And then it says determine the resistivity of the metal. So if I want to determine the resistivity of the metal, what am I going to have to do? Well, I need to know what the gradient is going to be equal to and so on. So I'm plotting a graph of R against Al. What is the formula first for resistivity? Or the formula that's got resistivity in there. What I know is R equals rho Al over A. Can I get this into Y equals mx plus C? Well, actually, they're quite nice because they're plotting R on the Y-axis. So there's very little rearranging for me to do. So if I put this into Y equals mx plus C, I know R is going to be equal, because Al is my other, Al's on my X, so Al's got to go over here, and it's basically going to be this. So when I plot R against Al, so this is my Y, this is my X, I know that my gradient is going to be this. So I'm going to show the examiner that I know that my gradient is equal to resistivity, resistivity over area. Okay, therefore, my resistivity is going to be equal to the gradient times the area. So I'm going to go back up to the graph and I'm going to just work out what the gradient is basically. So I've got to do the biggest good triangle and I'm going to show very clearly that I am taking a good triangle here. So it doesn't go through, or mine doesn't go through the origin. If you did it with origin, it doesn't look like it would. So I've just got to be careful when a line doesn't go through the origin. I can't start 0, 0. And I'm making sure that I'm making it very clear, whatever triangle I'm doing, that those are the points that I care about. Now, obviously, because this drawing is not very good, I can't bother to work out the gradient. So I mean, just work out what the gradient is for it, and then whatever the gradient is, it tells me that this is the cross-sectional area. So I'm just going to multiply the gradient by that number, and the answer on the mark scheme says that the resistivity should therefore be about 1.1 times 10 to the minus 6. And it's already in ohm meters. I've checked the units, and that's fine, so I don't need to do any conversions from there. There were no conversions on the axes because that's on meters, that's in ohms. So I've checked all of the standard tricks in there, and yeah, 1.1 times 10 to the minus 6, and they said plus or minus 0.1. So if you've got 1 or 1.2, any of those is fine as well. Okay, so there's some potential for confusion with this next question because it's giving me about the recorded values and actual values and stuff like that. So this is the way that I always approach these ones. I look at what is my final point that I'm trying to get to. So it's trying to ask me about the actual value of the resistivity. So every single thing that I'm going to be saying is about the actual value, actual value, actual value. And then I'll get to the actual value of the resistivity afterwards. So if it's saying that the one that was recorded, the potential difference recorded in the experiment was smaller, what does that mean about the actual value of the potential difference? Well, if the recorded value was smaller, the actual potential difference was going to be larger, obviously write it out in full. If the actual voltage was larger, well, what can I say about the resistance then? So V equals IR. If the actual voltage was larger, that means that the actual resistance is going to be larger. If the actual resistance is going to be larger, when I go to the this formula over here, what's the relationship between the resistance and the resistivity? Well, therefore, the actual resistivity must be larger as well. And another thing that you can kind of say as well is that just because I've got the graph as well, I could try to link this to the gradient as well and say the gradient is going to be larger. And because the gradient is larger, then I can use this one and say, well, if the gradient is larger, the resistivity is going to be larger as well. So I'm just saying all of those things, and I've just gone through in stages because I don't want to get myself mixed up about should I be talking about the recorded value, the actual value. So I just looked at this one first, and I'm happy that I've got the marks for this one. Okay, so as long as I'm taking a sensible approach here to electricity questions, nothing can go wrong really. So what should I do when I've got an electricity question? I need to remember that I'm just going to first label all the things that I know that's going to be drawn here, because sometimes they miss out labels on the diagram. They just give the information in the question as well. So is there anything that they've told me that I could like figure anything out from? So the resistor has a resistance of 120, that's already labeled on there, that's fine. Cells got an EMF as 1.5, that's labeled on. Negative internal resistance, that's good. And it says the potential difference across the diode is 0.62. So that's something that they kept a secret from me. So I'm going to label that on there that that is 0.62 volts. Well then, if this is 0.62 volts, now what can I work out? Well, it's a series circuit, therefore this must be 1.5 minus 0.62, which is going to be 0.88. And I've labeled that on there. Is there anything else I know? Well, from this, I can work out the current. Now I'm able to start doing it from over here. So the first thing that I've done is the voltage across the resistor is going to be equal to, like we said, 1.50 minus 0.62, which is equal to 0.88. And then if I'm going to get the current when I'm doing these, just make sure that you're remembering that I'm always saying when I'm using like V equals IR, I've got to say the V across this is the I through that and the R of that. The V of the total circuit is the I through the total circuit, the R of the total circuit. Well, because I've only got the R of the resistor, I haven't got the R of the total circuit. I only care about the V of the resistor, not the V of the total circuit. So when I'm saying V equals IR, so that's going to be 0.88 is going to be equal to I times R is going to be 120. And then this I therefore is going to be 7.33 something or other times 10 to the power of minus 3. Now, because it's a series circuit, I know that this is the current through the whole of the circuit. So the current through one of the things, the current through the whole of the circuit. So when I'm working out the power in the whole circuit, I'm going to say P equals VI or IV. And then I know the power of the whole circuit is the voltage of the whole circuit times the current through the whole circuit. So the voltage of the whole circuit is 1.50. The current of the whole circuit is what we've just worked out, 7.33 blah 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 times 10 to the power of minus 3. I put that in the calculator, and then the answer is 1.1 times 10 to the minus 2, and everything's in the correct units here. So I mean, it's asking me for it in watts, so I'm pretty happy. Okay, so hopefully you've had a read of this question, had a go at this question. Firstly, even though this isn't this exact question, I just want to remind everyone that this is an example of a potentiometer circuit. So the first thing that I'm seeing when I saw this question that stood out to me is like, oh, look, it's a potentiometer circuit, which they love as being the example, the pinnacle of all circuits, because I can get a range from 0 to, in this case, 6 volts. I can get the maximum range across there, which is the benefit of a potentiometer circuit compared to a potential divider circuit. And that's a very popular question that comes up. So just make sure you know what potentiometer circuit looks like. It looks like this, and the benefit of it for if that question comes up. I'm like, how do I improve the circuit or something? If they give you potential divider one, then just draw this one and say do this because it's better because you get the range. Okay, so what's this question actually saying? So it does change the reading from 0 to 6 volts, that potentiometer circuit, but the lamp stays off, the lamp isn't faulty. Basically, there's something wrong with the circuit, it's saying. So what is wrong with the circuit? Is there anything that stands out to me? Yeah, there is, and hopefully it stood out to you as well. That voltmeter is in series when it should be in parallel. So I'm going to say that that voltmeter is in series, it should be in parallel. Well, actually, when it says refine the circuit, I can kind of put that one afterwards. I'll say put it in parallel because it says explain the observation. So it's in series. So why does that matter? Well, I know that a voltmeter has got a really high resistance or infinite resistance. So if it's got a very high resistance or infinite resistance, therefore the current will be 0 or pretty close to 0. Well, if the current is going to be 0, the lamp's not going to turn on. So how am I going to refine the circuit? Well, now I'm going to say put the voltmeter. I'm just going to put V for voltmeter, and I'll just say parallel. Okay, there we go, lovely. Okay, so we've got the 6-mark question now, and I can see a graph in there. So straight away I'm thinking I've got to take readings from the graph, and I can see that I've got a potential divider circuit. So I'm already suspicious about the thing that I said earlier, that it might, like it could possibly be something about, oh, potentiometer circuit's better. It might not be, but that's just something that's in the back of my mind already. Okay, so let's have a look at what the question says. It says explain how it works and use calculations. So I mean, obviously I've got to break it down into both of those parts. So when I'm saying explain how it works, this is a potential divider circuit, and I just need to know my content for how it's going to work. And then obviously for the use calculations, I mean, that's pretty obvious what I'm going to have to do. I'm going to have to take reading from the graph and actually use some kind of calculation to make sure that I've got it right. Okay, so I will put the mark scheme up. I'll just go like that. There we go. But the like the way that I explain it might be easier than looking at the mark scheme, so I'll kind of have both. If you think that the mark scheme is easier, you just want to like pause it and just read it without my voice for the moment, then just do that. So just pause it now, and then I'm just going to carry on speaking afterwards. Okay, so explain how the circuit works. Well, I know I've got a thermistor in here. So if I've got a thermistor, what do I know about a thermistor straight away? I'm not going to write this down because there's just too much to write down, and then the video is going to be too long. So what do I know about a thermostat? The thing that I know about it is when the temperature is going to be increasing, I know the resistance is going to be decreasing. So that's the point I'm going to be making. Temperature increases, therefore resistance decreases. If the resistance of that decreases, I'm going to say the current in the thermistor has increased. If the current in the thermistor has increased, I also know the total current in the circuit has increased because it's going to be a series circuit. So now I've got a larger increase in the current in the series circuit. Now there's a couple of ways that you can therefore explain what's going on afterwards. You can do it in terms of ratios and say, what if the resistance has decreased of the thermistor? It's going to take a smaller proportion of the total voltage of the 6 volts. That's fine to get that right as well. But if you want to explain it or understand it in a different way, when we've just said the current of this whole thing has increased here, all of the current in the circuit has increased, while this fixed resistor is the same. So if I'm saying V equals IR for the fixed resistor, the R is the same, the current has increased, therefore the voltage across this resistor must have increased. If the voltage across this resistor must have increased, I also know from Kirchhoff's second law that the sum of the EMF is going to be equal to the sum of the potential difference. Well, the sum of the EMF is going to be 6 volts. The sum of potential difference is therefore also going to be 6 volts. Well, if this V has increased, in order to add up to 6, this V must have to decrease. So you can think of it in that way, that when the temperature increases, this V over here must decrease for the reasons that we've just said. And the other reason that you can say is because if the resistance has decreased, it's now got a smaller proportion of it in terms of ratios. And that's another way that we're going to get to the same answer. Okay, so I'm pretty happy that I've explained how the circuit works now. And then obviously I can say the inverse for when the temperature is going to increase instead. When the temperature increases, sorry, when the temperature decreases, the resistance increases, that's fine. When it says use calculations, obviously we already said at the start, I'm probably going to take something from the graph. So when it says about 200 to 300, obviously these are the calculations that I'm going to have to take. So I'm going to have to take the value of 200 and look at the resistance, which is that, and read that. Take it from 300, which is here, and then do a calculation with this number over here. And I've just got to make sure I'm doing those calculations properly. I'm not going to go through the calculations because I've already clicked, and therefore the calculations should be on the screen somewhere. But basically, I've got to make it clear that I'm doing those. And this is just about identifying how I knew in the first place. I knew because it said calculations, it said those numbers, and it's showing me a graph. So all of those are telling me, yeah, I'm going to have to do this one. I mean, if you see from the mark scheme as well, it says obviously you've got to do both of them or it doesn't count. Well, now the last thing, it says to discuss a significant limitation of this design. Well, even without doing the calculations, I can kind of see the obvious limitation is that between 2 and 300, there was very little change in the resistance. If there's very little change in the resistance, and also from the calculations that I've just done, I can see that there's going to be very little change in the voltage. And the fact that they've said it's got a full scale deflection of 6 volts, maybe that was made it a little bit easier. But to be fair, even if they didn't say that, I should know that that change in voltage is going to be so small compared to the full range of 6 volts. It's just so small, it's barely significant. Okay, so stationary waves question, explain how the stationary wave is formed. It's always the same thing. If this question comes up, you're always just going to say the same thing, which is there has to be 2 coherent waves traveling in opposite directions, and they always interfere constructively in the same position to produce antinodes and destructively in the same position to produce nodes. So for this one, when I'm applying it to this particular question, how are there 2 coherent waves traveling in opposite directions? Well, it's because the wave must be produced by the oscillator, what's the key thing that happens to make the second wave come in the opposite direction? The key thing that happened is reflected at the pulley. So now, and then I'm going to say that same thing that I've just been saying, that I'm going to say two, and I've got to make sure that I'm using the word coherent waves traveling in opposite directions. I'm not going to write the whole thing out because I can't be bothered, but just make sure that you're saying, and the thing you're going to be careful about is if you're saying, oh, they always interfere constructively and destructively to produce nodes and antinodes, or antinodes and nodes, even if it's that way around, that wouldn't be the marks. You have to say they interfere constructively to produce antinodes and destructively to produce nodes. So I need to say which one is which. So constructive for nodes and then destructive for antinodes. I'll just write it like that. That'll be fine. Okay, so for the next one, frequency of the oscillator is 60 hertz. Use figure 18.1 to calculate the speed of the transverse waves. So again, they've said that. They didn't really have to say that because I should know for myself if there's a diagram in there with numbers and stuff on there. I need to make sure that I'm using it. So how can I get this one right here? Well, what I need to know, the rule that I need to know about it, and again, this is something they test me a lot on, is the distance between one node and the next node is half a wavelength. So if I want one full wavelength, that has to be the distance between one node, miss that node out here, and then the next node here. So this over here is going to be one wavelength. Well, how am I going to get the length of that one wave? It's obvious. I can have a look at how many half wavelengths are on the thing. So on this thing, I've got half a wavelength here, half wavelength here, half wavelength here. So that means that I know 1.5 wavelengths must be equal to 0.54 meters. If that's the case, then I know, I'm just going to put that in my calculator and say that one wavelength is going to be 0.54 divided by 1.5. So one wavelength is going to be equal to 0.36 meters. And now I can just put that into the formula that I know V is equal to F times lambda. So I want the speed, so that's fine. The frequency, it tells me, is 60. Lambda I know is 0.36, and therefore the speed is going to be 21.6. And I round to two significant figures, so the speed is going to be 22. 3 marks. That's very, very nice. Okay, so this next question is quite a fun one. It's testing proportionality. They love to test proportionality, and hopefully we all love to do it as well. So let's give it a go. So the speed of the transverse wave is directly proportional to root of t. So I'm going to put speed fishy square root of t. There we go. I know that's true. And then it says the tension is increased by 14%, but it's asking me about the frequency. Calculate the potential increase in the frequency. Well, I've got nothing about frequency over here at the moment. So is there anything that I know about frequency that I can kind of put in here? Well, I know I need the square root of t in my answer because that's the information I've been given in the question. So that means I've got v left over, and I need to know something about f. Well, what do I know about any formula with f and v in there? It's obviously this one. So what have they told me here? It says the frequency is adjusted to get the same stationary wave pattern. Basically what they're secretly telling me is if it's the same pattern, it must have the same wavelength. So because the wavelength is going to be the same, I can say therefore v fishy f, v is going to be proportional to f because lambda is going to be constant. So now if I'm saying that v is proportional to square root of t and v is proportional to f, well that means that it must be the case that f is proportional to the square root of t. Okay, now I've got something that I can actually do in this question. So the tension is increased by 14%. Now, this might trip some students up because a percentage increase of 14. Well, how do I have a percentage increase of 14? I've got to multiply by 1.14. So I know that the tension has been increased by 1.14. So on this side, I have multiplied by 1.14. So if this side has been multiplied by 1.14, there's a root on that side, therefore there's got to be a root on the other side. So that means this must be multiplied by the root of 1.14. What is the square root of 1.14? I'll just put that in my calculator. The square root of 1.14 is going to be equal to 1.0677, blah, blah, blah. Okay, so what is that going to be equal to? That's an increase therefore of 6.8% if I convert that to a percentage. And yeah, so that's quite a nice question, and as long as we do the sensible thing of taking it in stages and saying what do we know, what's the secret information they're trying to give me, and the thing that kind of stood out for me here was same stationary wave pattern. Yeah, we got that answer, so I'm happy. Okay, so this next one is just recall really. State what is meant by the photoelectric effect is something I should just remember. But if I can't break down the words, so photo and electric. So photo shows that it's obviously photons. So it's going to be an EM wave, and then electric is going to be the emission of electrons. So it's going to be the emission of electrons when an EM wave is incident on the metal. And I've mentioned about it's got to be above the work function or above the threshold frequency on the metal and above work function or threshold frequency. Okay, how shall I answer part B? So it's saying the photoelectric effect can't be explained in terms of the wave model. So if they're saying it can't be explained in terms of the wave model, I'm obviously looking for something significant in this thing what I've just said about what is meant by the photoelectric effect that I can then link to why isn't it why can't it be explained in terms of the wave model? So what's the only thing that stands out to me really? Okay, the emission of electron, yeah, fair enough, that can be explained with both really, but it's about the threshold frequency. So the threshold frequency is standing out. So can the wave model say that there should be a threshold frequency? Well, no. So I'm going to get that one down first. So look how I've been very clear about what I was looking for in there because it asked me about the photoelectric effect. I've just defined it. That gave me a big clue. So the wave model can't explain why there's threshold frequency or can't account for the threshold frequency because in that model, so I'll just put W in the wave model, intensity should matter. Intensity should be a factor. Because if I've got more intensity, I've got more energy. If I've got more energy, the electron will be able to escape. But we've seen that that doesn't happen. So obviously the wave model can't be true. And now this is leading me towards the next thing that they love asking in A-level questions about, because intensity isn't a factor, why isn't intensity a factor? Well, that's because there's a one-to-one interaction. And very, very often by saying there's one-to-one interaction, it's like a separate mark by itself. So by saying there's a one-to-one interaction between a photon and electron, this is why why I know the photoelectric effect is going to be true. It's not the photoelectric effect. Why the particle nature of radiation is going to be true. So I'm looking for an excuse to say that one-to-one interaction. And then, I mean, is there a law, principle, formula I can use? Yeah, there is. I know that the energy of the photon is equal to the work function plus Ke max. And I'm just going to make sure that I define all those terms instead. So this is the energy of one photon. I'm making sure I'm making it clear that it's one photon. This is the kinetic energy of one electron. And I'm linking it back to that one-to-one interaction. I can be talking about just making sure that I know HF has got to be greater than the work function because it's the energy now. So if I'm saying work function, I've got to compare it to energy. If I'm saying frequency, I've got to compare it to threshold frequency. And then the other thing is about the kinetic energy. So what can I say about the kinetic energy? That is independent of intensity. The kinetic energy is only dependent on the frequency of the photons as well. So again, that's this thing that we're talking about. So if I'm saying any of those things, well, three of those things, I'm getting the mark here. The main thing I definitely want to make sure that I'm talking about is the one-to-one interaction that comes up all the time. But the rest of it, just make sure you're saying enough of those stuff to show a clear understanding. Okay, so I'd say this is a reasonably nice formula question as long as I'm being sensible about it. So the first thing, okay, nanometers, obviously I've got to be careful about that. It's giving me the work function. So there's only really one formula it can be. Well, it's always going to be this one. So I can start off by writing maybe HF equals work function plus kinetic energy max. But the fact that they give me the wavelength, instead of saying HF, what can I say? It's going to be HC over lambda equals the work function plus Ke max. Well, am I looking for kinetic energy? No, I'm not. I'm looking for maximum speed. So instead of kinetic energy max, what do I know that that's going to be? Well, I obviously should know that kinetic energy is going to be equal to half mv squared. I'm rubbing it out because I'm going to run out of space, but obviously in the paper you can write smaller and stuff, so you'll be able to fit it on there. Okay, now it's just a case of putting the numbers in. Have I got H? Yeah, I have. It's 6.63 times 10 to the minus 34. C is 3 times 10 to the 8. Lambda is 380 times 10 to the minus 9. I'm not being fancy by trying to put it in standard form. I'm just keeping it as it is. Have I got the work function? So the work function there is in electron volts. What does it need to be in? It should be in joules. So how do I get electron volts into joules? I'm going to say 1.1 times, and then 1.6 times 10 to the minus 19. So that's that, and then I'm going to say plus half mv squared plus half. It's an electron. What's the mass of an electron? 9.11 times 10 to the minus 31, and then times v squared. And I've put all the numbers in. I can simplify this if I want, if I'm not that confident by simplifying this side, taking away however I want to simplify it. But basically, I should then get the speed is equal to 8.7 times 10 to the 5. Okay, in this one, I think they've kind of made it a little bit obvious what the answer is by the way they've worded it, and they don't tend to word them like this anymore. They've said state this change if any. So this is already kind of leading towards, oh, like there probably isn't one. So now instead of saying state the change in if any, what they'll say is, or state what happens or something like that, state the effect. And if they're saying state the effect, the answer can be there is no effect, like that's fine, or it's unchanged or something like that. And obviously not necessarily just for this question, but whatever it is. If they give you two things that are independent of each other, and they can still say state the effect, and you just say it's unchanged. So here, state the change if any, or state the effect, the maximum speed of the electrons when the intensity is doubled. I know that the intensity is independent of KE max, and there's nothing in the formula for it that's got intensity in there. But I should kind of know this anyway, even if I didn't need to refer to the formula. But if I can't remember this, I would just refer what's happened. If I can't remember that, I would just refer to that formula here and be like, oh, it's got nothing to do with intensity. But because it's such a popular thing that comes up, hopefully I will remember. And then we can say, therefore, there's no change to KE max, or K, no, sorry. Does it say velocity, maximum speed to velocity max? Okay, there we go. Okay, so I think this is a pretty standard, just do you understand what capacitors are and how they work? So describe and explain how capacitor A and B are quite opposite charges. So basically I know that here's the cell over there, so when the switch is closed, which way the electron's going to move around the circuit? Well, I know that this side of it is positive, this side of it is negative, and the conventional current goes positive to negative, so the electron's going to go negative to positive. So the electrons will be going this way around the circuit. So I'll say electrons move clockwise around the circuit. Where they're going to go. So the electrons will go into plate A, join plate A. Oh, sorry, not plate A, plate B, because this one's B over there. And then when the electrons are joining plate B, an equal number of electrons leave plate A. And I can say, and then continue to go around the circuit or something like that if I want to do that. So therefore, plate B will be negative, and plate A will have the same magnitude of positive charge. And then, yeah, that's fine. Calculate the total energy stored by the capacitors. Well, even before I worry about that, it's pretty obvious what I'm going to have to do here. I can see from the diagram they've got like an awkward arrangement of capacitors. So if they've got an awkward arrangement, obviously I've got to try to simplify this diagram as much as I can. So the way that I'm going to simplify it first is these two over here. I can see that these are in series, and then obviously they're in parallel with the other one. So I'm just going to combine the series ones first. Now I know that if I've got capacitors in series, it's the opposite to resistors. So resistors, I would just add them together. Capacitors, the opposite. So I'm saying 1 over the total capacitance is going to be equal to 1 over 100. So this is just for the series ones, plus 1 over 220. And I've got to remember that is 1 over here, so I've got to do 1 over my answer afterwards. And then if I do that, what I'm getting is the answer is 68.75 microfarads. Okay, so now basically I've simplified it to two capacitors in parallel. So this one over here is the one that I've just worked out, 68.75 microfarads, and then this one is 500. And again, when it's in parallel, it's the opposite of resistors. So resistors, I would have to do this 1 over thing when it's in parallel. So capacitors, I'm just going to add them together, and so I can say 68 plus, oh sorry, 68.75 plus 500. So the total capacitance is going to be equal to 568.75. Okay, so now I've got a simplified circuit. That's essentially saying I've just got a circuit now that's got one capacitor, and it's got this capacitance, and that's microfarad. So obviously I've still got to be careful with my units. Okay, so now what am I looking for? I'm looking for energy. I've been given the voltage, and I've got the capacitance. What's the formula that links energy and voltage and capacitance? I know that energy is equal to a half CV squared. That's the thing that's got all of them in there. A half is a half. The total capacitance I've just worked out 568.75, but it's microfarads. Micro means 10 to the minus 6. And then voltage is 12. I put this in the calculator, and the answer is 4.1 times 10 to the minus 2. And I'm going to quickly pause this video so I can sneeze in peace. Terrible news, I didn't even sneeze, so that was a waste. And now I've got a sneeze somewhere in my body that wanted to come out, but never mind. So describe how the time constant of this circuit can be determined experimentally in the lab. So the first thing I'm going to do is just show the examiner that I know what's meant by time constant. So I'm just going to define time constant first. Obviously, you're not going to write that. You're going to actually do the definition. So what is the time constant? It is the time taken for either the initial voltage or the initial charge or the current in the circuit to decrease to 37% of its initial value. So just remember that thing about 37% time constant. Some students will sometimes get it mixed with half-life. So half-life is to get to 50% of whatever it was, of the number of atoms or the activity or whatever. Time constant is 37%. So I've shown the examiner that I know what time constant is first. Well, now that I've said the time taken for the voltage or the current or the charge to get to whatever, whichever one I'm going to choose, I've just got to say what's the equipment I'm going to use to measure it. So easiest one to do would probably be the current or the voltage, because with charge you're going to have to do some calculations with it, whereas voltage or current you can just read it. So what piece of equipment I'm going to use, I'm either going to need a voltmeter or I'm going to need an ammeter to measure, and then just whatever I'm doing. If I define it with voltage, I'm going to say voltmeter. If I define it with current, I'm going to say ammeter. And then what else am I going to need? I'm going to need a stop clock. And then it's just basically saying that same thing. So just what's the obvious thing we're going to say now? Charge it up to full charge, close the switch, and then measure the time it takes for the reading on the voltmeter to go down to 37% of original value, or the reading on the ammeter to go to 37% of original value, and so on. I'm still going to make sure that I'm saying repeat and take an average. And or some kind of idea of measuring more than one time constant. So after it's gone down to 37%, just let it keep on going. And when it goes to 37% of that value, then take another reading. When it goes to 37% of that value, take another reading. So it's just some kind of idea in there that, yeah, you do know that you should be taking averages for experiments, and then that one will be fine. Okay, so describe the similarities and the differences between the gravitational field of a point mass and the electric field of a point charge. So we've always said this one, when you're being asked for similarities or differences, particularly differences between two things, whether I know it or not, as long as I can define them, that's fine. So even if I didn't know the differences, I'm just going to define one of them or define both of them if I can, and then I can just figure out from there. So the first thing that I want to do is just make sure that I can define both. So what is the definition of a gravitational field? A gravitational field. It is the region around a body with a mass in which another body with a mass will feel a force due to its mass. And then for the electric field of a point charge, is the region around a field with a charge in which another body with a charge will feel a force due to its charge. So now from there, I can kind of see, because I've defined them, I can hopefully see some similarities and differences. So the similarities is they're both going to be fields, they're both going to be regions in which something feels a force, regions in which a force is felt. And then do I know anything about the force? What's going on here? Do I know anything about the force for both of them? Well, I know for a gravitational field, the force is going to be F equals GMM over R squared. For electric field is F equals KQQ over R squared. So for both of them, another similarity, I can say the force is going to be inversely proportional to the distance squared. The fields are both radial. I've got that because we're talking about point mass and point charge. So I know when I'm talking about the point thing, it's the radial field. I've got to use the radial formulae. And even though this isn't part of this question, it's just something that students sometimes make a mistake on. So be careful for that. That they will always mix up radial and uniform. So you just need to know when it's a point, always use the radial ones, the one with the square. When it's not a point, then obviously use the uniform ones. Okay, so I've done the similarities. What are the differences between them? Well, the differences between them are obviously that the gravitational field, when we were defining it, we said it arose due to a mass, whereas the electric field arose due to a charge. And then what's the other main or obvious difference between there? To be fair, I should have kind of put it in there as well. That the gravitational field is always going to be attractive because the answer was negative, whereas electric field can be positive or negative, just depending on the charges of your Qs. And I think that's going to be full marks for this one. But I mean, this was a bit of an easy example of it, maybe, but the point that you should be taking away from this practice question is that when we're talking about similarities and differences, and particular differences, always make sure that you are defining them first if you can. So even if you're stuck, don't panic, just do the definitions, give yourself a clue, pick up some of the easy marks, and then, yeah, you will hopefully do very, very well. Okay, so what's the two obvious things about why they would be separated? Well, the first thing is they must be repelling each other. So if they're repelling each other, it's because they've got like charges, they're both negative. As you can see, I'm not writing in full sentences. Um, but yeah, you need to. And then what's the other kind of obvious thing there? I can see they're in equilibrium because yeah, they're not moving, they're stationary. So if they're in equilibrium, what can I say about the forces of them? Well, I know that they're going to have the force of weight and the repulsive force and the force of tension are going to be all like equal. There'll be equilibrium under the action of the three forces. So we've got the weight going that way, we've got the repulsive force going that way, we've got tension going that way. And if I drew a triangle of these three forces, it would be in equilibrium. And I'm just going to make some kind of statement to show that I know that. Okay, I was really excited when I saw this question, so hopefully you were as well. Calculate the angle made by each side of the vertical. Because I've got these forces I get to resolve. I get to probably use sine, cos, tan, whatever it is. So, you know, we've got a lot of fun ahead of us. So let's have a go. Okay, so how am I going to know the angle made by each thread? So what are the things that I do know to begin with? Well, firstly, is there anything that I'm suspicious about here? Well, I can see the distance between the two charges is 2 centimeters, and this is in centimeters. Do I know anything about the amount of force that's on there? So I've got the charges over here, I've got the masses over here. So what are the obviously forces that I care about? I know that the first force of electric force, we can say, so the electric force that I've drawn on over here, so I'll just put that there, force electric, is going to be equal to KQQ over R squared, or I can say QQ over 4 pi epsilon naught R squared. So what is the Q? Well, both of them are minus 4 times 10 to the minus 9. So I can say minus 4 times 10 to the minus 9. And when I'm multiplying them together, because they're both the same, I can square it. So just be careful. Some students will put times 2, but I know it's not that. And then divided by 4 pi epsilon naught, I can't be bothered to write out epsilon, like the full number, just get it from the formula sheet. And the distance is 2 centimeters, so that is 0.02 meters, and I've got to make sure that I'm squaring that. I put that in the calculator, and the answer is, that's squared by the way, and the answer is 3.596 dot 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 times 10 to the minus 4. Okay, so that's the electric force. Now the force of weight, so mg, is going to be, well, I've just said it's going to be mg. And what is m is 6 times 10 to the minus 5. What is g is 9.81. So what is mg is going to be equal to 5.886 times 10 to the minus 4. Okay, so I've got those two forces there. So let's just kind of draw the diagram here. Now, do I know anything about tension? Possibly, like, I mean, I could work it out from those two forces, but it's not asking me to do that. It's just asking me to work out the angle. So what have I got in this situation? I have got, I'm just going to draw it there. So we've got the weight that's going down that way. So I'll just put weight there. I've got the electric force, which is going here. And then we said I've got the tension that's going here. And I know because they're in equilibrium, I should be able to draw a triangle of forces. When I've got a triangle, the rule is the arrows have got to be top to tail. So all of these arrows are coming from the same point. They can't do that. They've got to come from top to tail. So I've just got to choose how I'm going to draw this triangle. It doesn't really matter which way I'm doing it. But I know it's going to be a complete triangle because it's in equilibrium. And they kind of gave me a clue about that in this one. So the weight is going down there. So this is the weight, and I've already worked out the value of that side, but I'm just going to call it W there. Then I know the electric force is going this side, and I'm going to just label that electric force. And again, I know the value, which is over here. And then the tension is going to be here. It's got to go back to its original place. So I'm going to draw tension there. Now, what angle am I looking for? It's the angle with the vertical. So this is the angle here that I'm looking for. Because this is essentially the angle of the string here. So I can do that now. So how am I going to work out the angle? Well, I've worked out this, I've worked out this. I don't care about this. So in relation to this angle, what are these things over here? So I've got the opposite and I've got the adjacent. So when I've got opposite and adjacent, I know it's going to be tan. So I'm going to say tan theta is equal to the opposite, which is the electric force, which is 3.596 blah 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 times 10 to the minus 4 divided by the adjacent, which is 5.886 times 10 to the minus 4. I can put that in the calculator and it gives me that theta is 31. So I'm just going to put that there. How exciting. Okay, so draw 5 lines to represent the electric field. Well, I can see that they're parallel plates. If they're parallel plates, it's got to be a uniform field. If it's a uniform field, the lines have got to be equidistant. So if I had to write it, I'd use the key term equidistance. If I've got to draw it, I just draw lines that are equal to each other, and they've got an equal distance from each other, and they've got to be parallel. So it says draw 5 lines. So hopefully I can count to 5. Let's see, 1, 2, 3, 4, 5. They're not quite equidistant, so that's rubbish. So what I'm going to write down here, just to make sure the examiner knows, is I'm going to write the key term equidistant. So if it's a bit iffy between, like, for example, these ones look a bit crap compared to those ones, I'm just going to write this word so the examiner knows, so that if there's any doubt like there is with this one, the examiner knows, okay, yeah, he meant to draw them the same distance apart from each other, and will hopefully give me the mark there. Obviously, I'm going to try to just draw them properly in the first place. I'm saying if you're not sure or whatever, and even if you do think they look equidistant by eye, I mean, it's not going to hurt you to write the word. And the other thing I didn't quite make it clear is like why the arrow is pointing this way. Well, it's because I've seen that this side here is positive, this side here is negative. So this plate here must be positive, this plate here must be negative, and I know that the electric field lines are always going from positive to negative. Okay, so this next question looks like it could be quite tricky. Maybe some of you find it a little bit easy, but we're going to go through the process that we've learned in the lessons just to make sure that if you do get a difficult question in the exam or one that can be potentially difficult, we're just reminding ourselves of the process that we've done and how we can make sure that we're problem solving properly. So what am I going to do first? So I'm looking for the final speed of the electron. So the fact that it says final speed here is kind of making me suspicious that there's some initial speed in there that I need to be aware of. Now, like I said with one of the earlier questions, they've kind of made it obvious with their phrasing that, yeah, there is. In the real exam, I mean, if they just had calculated the speed of the electron as it leaves, it's kind of your job to know that that's a final speed. And more recently, they've been doing that kind of stuff. So just kind of be aware of that. Okay, so I'm pretty stuck on this question. I don't really know what I'm doing, so let's just see what I can do. So the first thing, just go through everything. Well, I'm looking for the final speed. So I'm looking for V. What have I got? It says a separation of 1.2 centimeters. So I've got some kind of distance in there. And it's in centimeters here, so I've just got to be careful that I'm doing a conversion now in case I forget later. I've got an electric field strength, so I'm going to write down E. The fact that it says it's an electron, what do I know when they name a particle? I know that I've got a mass and I know I've got a charge. So I'm either going to need one or the other, or I'm going to need both. And then it gives me here, it had a horizontal velocity when it was going in. So I know that I did have a horizontal velocity or initial velocity like I suspected. It's a bit more obvious in this question, but just look at it in the real exam. It might be the initial velocity is 0, or there's some other kind of way, like the previous question, where you've worked out an initial velocity as it was coming in, or something like that. So just be aware of those things, that what they can do in the real exam to make it a little bit more tricky. But here, yeah, it seems, I mean, they've just told me the answer. It's a bit more straightforward, this part of it. Okay, so V is the most important thing that I care about. Is there a formula that's got V and all of those things in there? No, there isn't. So what am I going to do next? Is there anything with V and any of those things in there? It still doesn't, anything doesn't come to mind. It's still pretty difficult. So what am I going to be doing? I'm just going to do anything that I can and just hopefully I'm going to give myself clues that way. So the fact that I've seen parallel plates and the fact that I've got E and D in here, I've done enough past questions to know that when they're giving parallel plates and they're giving me an E and they're giving me a D, the reason is because they want me to work out V. So even if I don't know why, as in V for voltage, not V for final velocity, even if I don't know why, I mean, I might as well just do it. It's possibly I've got a method mark here and I might give myself a clue. So I know that E is going to be equal to V over D. Well, I know those numbers because it tells me that E is 1500. V I don't know because it's what I'm looking for, and then D is 1.2 times 10 to the minus 2. So I'll put this in my calculator and I get my V as being 18 volts. Okay, so I can put V over here with all the list of things that I've got now. Can I do anything with this? Well, actually, now that I've worked out V, because remember the fact that I said an electron earlier, I knew the mass and I knew the charge. Well, now I've got V and Q. Is there a form of V and Q in there? Yeah, there is work done. And this is one of the things that I kind of alluded towards at the start of this question, that we've been doing stuff in lessons and in previous questions and stuff like that, that when you're really stuck on something, you don't know how to do it, if you can jam energy in there, then you give yourself a pretty good chance, because a lot of difficult questions, they can be done in terms of energy. So even if I didn't spot it this way, the way that I've done it, I could have just thought, is there a way of getting energy? Is there a way of getting work done? And like I've realized now, yeah, there is. So I put those numbers at 18. What's the charge in electrons? 1.6 times 10 to the minus 19. So I put that into my calculator. So 18 times 1.6 times 10 to the minus 19. And I know that the answer is 2.88 times 10 to the minus 18 joules. Okay, so I know that work done is the same as energy transferred. That's another thing that always, I'm saying it in my head over and over again, because it's another thing that students trip up on. And as long as I can make that distinction very clear in my head, I've always got a chance of giving myself a clue. So if I'm saying work done is energy transferred, I know that this much energy has been transferred either to or from the electron. So is it to the electron or is it from the electron? Because it had an initial speed, and I can work out the initial kinetic energy then. KE initial, because I know it's half mv squared. And I've got all the values that I can. So half is a half, m of an electron is 9.11 times 10 to the minus 31, and then V, it tells me here, is 5 times 10 to the 6. If I put that all in the calculator, I get my initial kinetic energy of 1.13875 times 10 to the minus 17. Okay, so it had an initial kinetic energy, and I'm saying this much energy is transferred. So has it gained that much kinetic energy or has it lost that much kinetic energy? Well, let's have a look at what's happening. And I can do it in terms of, I'm looking up here now. So I can see that the arrows are going that way, and I've got an electron that's going with the field. So if an electron goes with the field, it's losing energy. But that, to be fair, to me, I think that's a little bit too complicated. I might get it the wrong way around. I might forget. So I'll just do it a very simple way and say this plate is positive, this plate is negative, an electron is negative. Therefore, it's going this way, because it tells me, and it just tells me in the question it's going that way. So it's going towards positive, it's going towards negative. It's going to be repelled, therefore it's going to slow down. So if it slows down, it's going to lose energy. So it started with this much energy I've got over here, and it lost this much energy. So how much energy did it have at the end? So 1.13875 times 10 to the minus 17 minus the 2.88 that we've just worked out. And the energy that it's got at the end is going to be equal to 8.5075 times 10 to the minus 18. Well, now hopefully everyone's sitting there going, oh yeah, I know the answer now, I know what to do, even if you weren't too sure before. Well, if you've got that kinetic energy at the end, I can just put that equal to half mv squared. And then basically I'm going to know the answer. So half times 9.11 times 10 to the minus 31 times v squared. And I'm just going to put this in the calculator. So divided by 0.5 divided by the mass of an electron, and then I've got to take the square root of the answer, and then the square root of the answer is 4.3 3217 blah 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 times 10 to the power of 1, 2, 3, 4, 5, 6. So I've written the full number, or fullish number off the calculator, a lot of the significant figures, and now I'm going to give it to two significant figures because there's no reason to give it to more in this question. So the final answer is going to be 4.3 times 10 to the power of 6. And that was a pretty difficult question, but look how we just took that approach of I didn't panic, I just didn't go, oh, I'm going to sacrifice these 3 marks. I just did what I can do. I've used my experience to go, okay, there's parallel plates, what they normally ask me for parallel plates. I don't know what I'm doing, so I'm just going to try to jam energy in there, and I've used all of those techniques, and I've got the answer now, which I'm pretty happy with. Okay, so what's the first thing that is obvious to me here? I can see it as a circular motion question. So as soon as I see it's a circular motion question, I won't even bother looking at the question yet because I already am predicting what they're going to test me about, what they're going to ask me about. I'm going to need to know, firstly, that F equals either mv squared over r or F equals m omega squared r. I also know that F equals something else that I can equate to that. And the other thing that I know is that that force goes to the center of the circle. So they're the 3 main things that they're going to test me on in any circular motion question that I need to be aware of. Okay, so let's have a look at the question first. State the direction of the force acting on a positron. Well, they're just testing me on this one straight away. So I'm going to say the force is going to the center of the circle. Okay, and explain why this force does not change the speed of the positron. Well, one thing actually I'll just say it now as well, that the fact that it says positron, just remember I'm already suspicious about this, that they give me the values about something about speed, radius, and then the positron, I know I've got the mass and the charge that might be useful to me later, and I might mention it now, put it there just so I remember something if it does come up later. When I'm saying explain why it doesn't change the speed of the positron, well, what do I know about this thing? And even if I'm not too sure about what the answer is, I just know that the force is acting perpendicular to the motion. And this is probably enough to get me the mark, to be fair, but it's important that you understand it also, like, why would that matter if it was acting perpendicular to motion? Well, I know that, let's just say here's the positron at whatever point it's at. If it's always acting perpendicular, let's just say it's going that way. So acting perpendicular would be here. So if I want to get this force in the direction of the motion, I've got to resolve it basically. So I've got to take the cos of the angle that I'm going through. Well, if I take that cos of 90, what is anything cos 90 is 0. So what is the force in the direction of the motion? The force is going to be 0 in the direction of motion. And I could maybe add this here as well. But to be fair, even just with this, I will probably get the mark anyway. But yeah, just to make sure that you're understanding it, it might be worth saying that part as well. Okay, so when I'm saying calculate the magnitude of the magnetic flux density in the magnetic field, again, I was kind of predicting that this was going to come up. It's probably going to be something to do with these formulae over here. Well, there's a question mark 1 over here because depending on the circular motion question, I don't know what the other force is going to be. But I mean, for this one, I've got enough information to figure it out. So the first thing that I'm always going to start with is F equals mv squared over r. And I'm starting with this one just because I prefer it. Like, I just like this equation better. There's no reason why it is better than this one. And I might want to start with this. And some equations I might have to start with that. Some questions I might have to start with it. But I just prefer this one. So I'm just going to start with this one. Now, I know that I'm going to need to put that F equal to something else. And what is that F going to be equal to? Well, I can either do it by looking at the information that I've got, looking at what the topic is and seeing what the force is going to be for that. But in this question, I'm looking for the magnetic flux density. So I'm looking for B. And I know that I need some kind of force in there. So is there a force that's also got B in there? Well, yeah, there's F equals BQV. So now I know I can just put these two things equal to each other. So I know that mv squared over r is going to be equal to BQV. Because I'm looking for B, I'll just rearrange it to say B equals. So I'm going to say B equals mv squared over r, and then the B and the V go on the other side, so BV over here. That V cancels with that V. So this is what I'm saying, like, this is the answer I've got. Now I've just got to hope that I've got all of these things. Have I got the mass? Yeah, I do, because it's a positron, and a positron is just an electron, but obviously a positive version of electrons, an antiparticle version. So it's going to have the same mass, which is 9.11 times 10 to the minus 31. Have I got the speed? Yeah, I do, because it tells me in here. So I can just put that straight in. It's not like other questions where I have to like work it out based on kinetic energy or something like that. I don't know. Or if it's been accelerated in a different part, whatever. Have I got the radius? Yeah, I do. And I've just realized I wrote B there instead of Q. so the radius is up here, and have I got the Q? Yeah, I do. The Q is the charge on a positron, which is going to be the same as the charge on an electron, 1.6 times 10 to the minus 19. So I'm just going to put those numbers into the equation. Oh, sorry, put it in the calculator as well. Whoops, I was just trying to brush some hair off my iPad and I swiped the screen by mistake. And so B is going to be 1.6 times 10 to the minus 2. That's rounded. I just couldn't be bothered typing into the calculator, so I just got it off the mark scheme. But that will be fine. Okay, so what's standing out to me in this question, the fact that it says positron interacts with stationary electron. So I can see the fact positron and electron, I already was kind of suspicious about this earlier, because when it says positron, I'm already thinking, yeah, there's going to be some annihilation somewhere. The fact that it says stationary electron, I'm a bit suspicious about that to begin with, because I'm thinking, oh, if the electron is stationary, I know that still the total energy at the start has got to be the total energy at the end. So I'm thinking, okay, the positron was moving with some kind of kinetic energy first, but thankfully in this question it says assume the kinetic energy of the positron is negligible. But in your exam it might not say that. So I was suspicious about this first when I'm reading the question. The electron is stationary. It doesn't mean the other thing is. So if it didn't say this, I would have to work out the kinetic energy of the positron first, and add them together and like say, okay, this was the initial kinetic energy like we did with the previous question, but yeah, here it's negligible, so it's fine. Annihilate each other, so straight away I know that it's going to be E equals mc squared. And the fact that they've said here it's quite nice, two identical gamma photons traveling in opposite directions, again, even if it didn't say two, like we should know that it's two when there's the annihilation that's happening, because of the conservation of momentum. We know that they've got to go in opposite directions to conserve momentum, so they've told us it's two here anyway, so that's okay. Okay, so what am I going to have to do? So I know that the energy of the positron is going to be mc squared, and the energy of the photon is going to be hc over lambda, because I care about the wavelength of it. Now, because there's two photons and there's also like a positron and electron, there's two particles, I can say 2mc squared is going to be equal to 2hc over lambda, but obviously those twos are going to cancel each other out, so if I didn't say that, it's not really the end of the world. Now I'm looking for the wavelength over here, so how am I going to get the wavelength? I'm just going to put the wavelength up there, and then I'm going to say it's going to be hc over mc squared, and then that c is going to cancel with this c over here, so I'm going to get the wavelength is h over mc. And now it's just a case of putting numbers in. So h, I know the Planck's constant, I can get it from the formula sheet. M, the mass of an electron, is the same as the mass of a positron, which is why I did the two here and cancel them out. And then c, the photon is going to be moving at the speed of light, so I'm going to put 3 times 10 to the 8 for the photon. I'm just going to put that into the calculator, and then the answer it gets me is 2.4 times 10 to the minus 12. So this question here, again, is a little bit easier than might come up in the real exam, so that's why we took a bit longer to talk about what could possibly come up, what you should be looking out for. And just the main thing is this thing over here, that the fact that it was moving first, just be aware of that if you have to add another energy to it. In this question we didn't, but who knows what's going to happen in the real exam. Okay, so we've got the 6 mark question over here, and to be fair, this seems like quite a nice one. The only thing that is standing out to me first is this graph is like a kind of unfamiliar one. We've never seen a graph before of energy against half thickness. So I just need to be aware here that the energy is in mega electron volts, the half thickness is in millimeters. And then the question is saying, describe the experiment to determine the half thickness, and how would you use the results to determine the energy? So basically, if I can describe in this part over here, how am I going to get the half thickness of something? Then I can say, okay, I'm going to basically use the graph and do the line of the graph, whatever it is, blah, blah, blah. And then from there, I can get the energy. And then it's saying about the equipment and safety and how the results might be improved. There's nothing really in that I can say that isn't already in the mark scheme, apart from the fact that because it says determining the half thickness, the first thing that I'm going to do is just make sure that I've got a statement in there so that I can show the examiner that I know the definition of half thickness. And then other than that, I'm pretty sure that anything that's in the mark scheme is just going to be pretty reasonable. And I've already said be suspicious about the graph. I'm looking at that, so we can just go like this, and then I think, yeah, just read that, and I'm going to stop this and just pause it if you need to check your answer, and we can move on to the next question. Okay, so let's take a look at this next question here then. So there's quite a lot of information here, so it seems that it might be pretty complicated, and it's a 4 mark question I can see, so there's probably going to be a few stages of the calculation. So let's have a look at the information that I've been given. I'm going to see if there's any clues that I can use from there. So firstly, it says 9.9% here. So I'm thinking, okay, there's going to be some either scaling up or scaling down or something like that that I'm going to have to use to get to my final answer. The fact that it says half-life, I'm already thinking, I know I'm going to have to work out the decay constant lambda, because all of the equations with half-life really in my radioactivity section of my formula sheet, they've all got lambda in there. And then the fact that it says molar mass, I'm thinking, oh, bloody hell, I'm going to have to do some chemistry. I'm going to have to remember the thing that I've got from that. But thankfully, they've given me in proper physics units. So, I mean, even if it didn't give me this, I should know from the 18 that it's going to be 18 grams per mole, which is the same as 0.018 kilograms per mole. But I mean, at least they've given me that. So let's give them some credit. At least they've done that. Okay, so it's given me the initial activity as well, and it's in mega, so I know that there's going to be a times 10 to the 6 in there, and it says use the information given to calculate the initial mass. So the fact that I've been given the initial activity and the initial mass, I'm kind of ruling out these equations, the one that are like A equals A naught e to the minus lambda t, and the n equals n naught ones as well, because these are to do with like, oh, after a certain period of time, how much is left and stuff like that. And because they've already given me the half-life and it's in proper units and stuff like that, I don't need to work out the half-life from here. Some questions I might have to be like, oh, what's the half-life going to be? So that's when it goes from 50% from 100 and start putting in numbers out. I know I'm not going to have to do any of that to get the to get lambda or t or anything like that, because it basically just tells me that. So at least that's something. And then because it's saying about like activity and mass, I know that mass is going to be proportional to the number of particles. So this is leading me towards this equation over there, because it's giving me an activity. And like we're already suspicious about, you know, I'm obviously going to have to work out lambda, and that's going to be the case for any radioactivity question. So we might as well just do that to get started. So how am I going to work out lambda? I'm going to look at my formula sheet if I can't remember the formula, and I know that lambda t half is going to be equal to ln2. So I'll rearrange that to say lambda is going to be equal to ln2 over t half, which is in seconds, so I don't even need to worry about, oh, do I have to convert it? What's my unit? It's just that everything's going to be in the proper units. So 6,600, and I'm going to put that in the calculator, and the answer that I get for lambda is going to be 1050 times 10 to the minus 4, and proper units s to the minus 1. Okay, so now that I've got that lambda, I'm thinking, okay, what can I do with that? I might as well go to this equation and just see if I can do something with that. So have I got the initial activity? Yeah, I do. I'll just rearrange this now to be fair. So lambda is going to be equal to A over N. Have I got the initial activity? Yeah, it's 400 times 10 to the 6. I've underlined the M so I don't forget. Wait, sorry, I'm looking for N, aren't I? So N's over here, lambda's over here. Have I got lambda 1.050 times 10 to the minus 4? I'm going to put this in the calculator, and it gives me the value of n as 3.809 times 10 to the 12. So I'm saying that this is how many particles I've got now. So I've got this many particles of fluorine. So what can I do with this now? Because remember, I'm trying to look for the mass of FDG. So if I want the mass of FDG, I know there's going to be some scaling up from this, so it's going to be sensible to get the mass of fluorine first. And what do I know about getting the mass in there? Well, because I've already seen the molar mass thing, I'm start thinking, okay, I better do some of the chemistry stuff. So what are the things that I know? I know that mass over molar mass is going to be equal to number of moles. And what else do I know? Because I mean, number of moles isn't that helpful in this question. I need to know how am I going to get that into actual number of particles. Well, I also know that the number of particles is going to be equal to the number of moles, and I could have just written n to be fair. Why have I written that twice? And multiplied by Avogadro's constant. So I know that these things are true. So how am I going to get the mass from here then? Well, let's just put it in there. So I've got the mass from my top equation. Then this number of moles over here, I'm just going to change it to, by using the second equation over here, to n divided by Avogadro's constant. And then I'm going to bring this over here. So that's going to be multiplied by the molar mass. And have I got numbers that I can put in here? So have I got n? Yeah, I do. N is over here. Have I got Avogadro's constant? Yeah, I do. It's 6.02 times 10 to the 23. And have I got the molar mass? Yeah, I do. They've actually given it me, even though I should know that from the fact it's called fluorine 18. So I'm going to put those numbers in the calculator, and the answer that I get from mass is 1.1389 times 10 to the minus 13. I'm going to have to start writing down here in part C, but I'll just rub it out afterwards. So I've got this mass over here, so that's fine. And that mass is going to be in kilograms. Now, what has been decaying, the thing that's been decaying is fluorine 18. So I know what's the mass, what is that the mass of, sorry, that's the mass of fluorine 18, which is equal to 1.1389 times 10 to the minus 13. Okay, so if that's the mass of fluorine 18, I care about obviously the mass of FDG. So they've already said 9.9% of the mass of FDG is fluorine 18. So basically this is 9.9% of the total value. So if that's 9.9% of the total value, how am I going to get to 100%? Well, if you're more confident with maths, you can just say, oh, I'm going to divide by 0.099 and then I'm going to get the answer. And then that will be the correct answer. Yeah, that's great. If you're not too confident with it, a way that you can kind of do it and think about it is if you either use a formula. If you know a formula, you can get a formula from there. But a very simple way that I've seen a lot of students do is just how can I scale that up? Well, first just scale it down to 1%. So I'm going to say 1.1389 times 10 to the minus 13 is equal to 9.9%. Well, then in order to get 1% of that, I'm just going to divide by 9.9. So I'm just putting this in my calculator now because I can't do this in my head. So divide that by 9.9. So I know therefore that 1% is going to be equal to 1.150 blah 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 times 10 to the minus 14. Well, if that's 1%, I'll multiply that to get 100. So therefore 100 is going to be 1.150 blah 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 times 10 to the minus 12. And that's what I'm looking for. I'm looking for 100. So if you were more confident with maths and you just did that division first and just said, oh, I know that it's got to be divided by 0.099, that would be the same answer. But it's just another way that you can do it if you are not that confident with your maths. And now I am going to round this to how many significant figures? It'll be 2 significant figures, everything else is 2. So that is going to be 1.2 times 10 to the minus 12, and that's in kilograms. So I'm happy that that's right now. Okay, I'm going to rub all of this stuff out, so I've got space to do part C. Bye. Okay, while I was rubbing that out, I've just seen that I've got an option of writing in a fountain pen. And because this seems like a nice fancy pants question rather than a like physics question, ethical issues, I'll just use a fancy pants pen as well while I'm doing it. So that'll be nice, hopefully. Let's see. Okay, so discuss the ethical issues. Okay, so it's not like a proper physics question that I'm going to have to do, but I mean, I want to get the marks for it anyway. So because we're talking about the nearby on-site particle accelerator, what's the main thing? Is something about it's inaccessible. Oh, this is not as fancy as I thought it was. Well, never mind. So what are the things about it being inaccessible to everyone? Things that they kind of like people saying it's like a postcode lottery. I wish I hadn't done this now, but it's too late. So postcode lottery in terms of like, are people living in certain locations or richer locations might be more likely to get people in more affluent areas. So there's disparity between the kind of people who are going to be getting treatments. It's going to be up to the doctors. So the doctors are going to be having to make decisions about who's going to be getting the treatment, who are they going to send. If it's in like areas that can't afford it, they might have to be sending some patients to different areas, and they're going to have to make the decision as to who would be getting it and who wouldn't be getting it. I mean, that's anything kind of sensible along those lines. I'm going to change my pen back to the normal one because this is not nearly as fancy as I thought it would be. What a shame. Okay, so back with the bog standard pen, what is meant by the piezoelectric effect? This is just something that I should know. So I should know that the piezoelectric effect is when I apply a voltage across a crystal, it's going to expand, and then if I apply a voltage in the opposite direction, it's going to contract. So I'm just going to say define that. I can't bother to write it out. Okay, so some good news. I finally sneezed. So all of you who've been sitting there thinking for a couple of questions ago, oh my God, I hope you managed to sneeze. I have, so that's great for everyone. Okay, so now we can have a look at this question now, nice and relaxed with no sneezes inside us. What's it saying? So the first thing, I've got a graph question, so I'm going to look at the axes, and it says, right, I've got Z over here, so I've got the acoustic impedance, and I have got the reflected intensity on this axis. So, I mean, this question seems pretty hard. Explain why the curve has a dip. I don't really know. So how am I going to approach this question to begin with? Well, because the axis says about reflected intensity in Z, is there a formula that kind of links those things together that I can start with and maybe give myself a clue? And yeah, there is, because I know that the percentage reflected is going to be equal to Z1 minus Z2 squared divided by Z1 plus Z2 squared. Okay, so now that I've done that, is there something that I can say like, why does it have a dip? Well, what's the significant point on there? The point where it's 0 I can see is 2.5 times 10 to the 6, and they've also given me this 2.5 times 10 to the 6. So I've got the equation to give myself a clue, I've got the significant number to give myself a clue, and I think probably from here I can figure it out, because what's significant about the fact that this is where the dip is at 0. So when there's 0 reflected, is because it's 2.5. Well, if I apply that to this equation there, I'm going to say there's nothing reflected, or I can just state the obvious first, basically, if I'm still not too sure about it. So nothing reflected at z equals 2.5 times 10 to the 6. Why is that the case? Because if I'm looking at this equation over here, well, both of those numbers minus each other is going to be 0, and 0 divided by anything, oh, I should have, because it's percentage, I should have put times 100 here, and 0 divided by anything is going to be 0, so 0% is going to be reflected. So I'm going to say when z numbers are the same, there'll be nothing reflected. I can use the key term impedance matching. The impedances match, the acoustic impedances are matched, anything like that. And then when it's anything less than that, so anything else, there's some kind of difference, and therefore there is going to be some proportion that's going to be reflected. And when I'm moving further away from this point, well, obviously the difference is going to be larger. If the difference is going to be larger, that number is going to be larger. If that number is going to be larger, the percentage is going to be larger. I haven't got space to write that whole thing down, but maybe you have or had. Okay, so where do I think I'm going to get the marks coming from in this question? Well, firstly, it says describe and explain. So when I'm saying explain, I'm going to go law, principle, formula first. Is there a formula that has got the about measuring the speed of blood in artery? Yeah, there is. So I know probably going to get 1 mark for stating the formula, hopefully. Then it says state one major advantage. So the fact that it says state suggests it's going to be like 1 mark, and one major advantage, that's going to be so one thing together here for saying that advantage. So there's 2 marks in total, which means I've got 2 marks left over for the describe part. So I'm going to have to give like 2 detailed things, maybe 2 separate points in the description part to get the 2 marks. So that's how I'm thinking I'm breaking this one down. Okay, so as we always do when it's an explain question, just go law, principle, or formula first. In this case, there is a formula, so I'm just going to write that down and try to get the mark from this. So the formula from my formula sheet says change in frequency over frequency is going to be equal to 2v cos theta divided by c. And I just need to show the examiner that I understand what this means. So the v is going to be the speed of the blood, the c is going to be the speed of sound in blood. The change in frequency and the frequency they're going to be from the transducer, and I'm just showing the examiner that I know all of that kind of stuff and I can say that stuff in the question. So now I know I'm probably going to have to make 2 points for the description. So what I'm going to say for the description, well, firstly, there's cos theta in there, so that's suggesting there's some kind of angle, and I know I'm going to have to use the transducer, so I'm going to say the transducer is placed at an angle, and it says in an artery, so I'm going to say an angle to the artery. And then, well, what's going to happen from there? I know that it's going to give out ultrasound, and that ultrasound is going to be reflected, and then it's going to be detected at the same. So it's reflected from the blood cell and detected from the transducer as well. Now, I should probably have said earlier as well that the ultrasound is sent out in pulses, because I don't want the transducer to be still transmitting when it should be detecting. So sent out in pulses, and then that's reflected from the blood cell, detected the transducer. Okay, that's fine. I know there's going to be change in frequency. I'm just going to write it like that. So change in frequency of the ultrasound, and then the equation can be used to determine what am I looking for? Determine the speed of blood. So determine the speed of blood, and I've got that. So I'm pretty happy that I've said, I mean, I've given the formula here. I should have said 2 things for the description. I've kind of said 3 there, and this last one doesn't count because I gave the equation earlier. So I think, yeah, out of those 3 things, hopefully 2 of them are going to get me the marks I'm getting from that. And the last mark has to be about stating an advantage, and what is the advantage of this like ultrasound. It's always going to be the same thing, that it's going to be non-invasive. And to be fair, I'm pretty confident that that's going to get the mark. But then I could also say stuff like, oh, why does that matter? So it's like less painful, less recovery time, minimizes the risk of infection, all of that kind of stuff. So I'm pretty happy that I've got 4 marks from this paper, from this question, sorry. Hopefully more marks in the paper. Okay, that's it. Good.